Okay, I'm going to see how this goes. If the whole video falls apart and the camera smashes, it's because my camera stand is a massive bodge job of a plastic box, some sellotape, a set square, and a box set of the Little Miss books. So we'll see what happens. Okay, so what we're going to do today is dynamic equilibrium and reversible reactions. So what do we mean by that? I'm also going to try and do this with no editing, so we'll see. So dynamic equilibrium and reversible reaction. So reversible reaction. So you've got your standard reaction. A plus B makes C. This important arrow. In a reversible reaction, we don't use the arrow. We use a reversible reaction symbol, which means A and B can make C, but it also means C can make A and B. So it's like having this reaction, A plus B makes C, C makes A and B, and you just combine them together, so you don't need to use those, and you get that. So that's a reversible reaction. We use that symbol. So if you see that symbol, it's symbol for a reversible reaction. Now, this bit, this phrase, dynamic equilibrium. So equilibrium means balanced. I'm going to try and write it. It'll just take too long. Equilibrium means balanced. Dynamic means constantly moving, constantly changing. So we've got something that's constantly changing but balanced, which seems a bit strange and opposite until you consider the specifics of it. So as an example, one I put earlier, we've got people who don't own a house and people who own a house. And in this imaginary example land, no one knocks down any houses, no one builds any houses, and the amount of people stay the same. So if we've got 100 houses and 1,000 people, then we can have 900 people don't own a house and 100 people who do own a house. So the amount of people on each side stays the same, but the specific people change. So if somebody buys a house, that means somebody has to sell a house. So Jeff buys a house, goes into this group. Who did he buy a house from? He bought it from Bob. So Bob doesn't own a house anymore. So he goes over there. So we have the same number of people on both sides, but if you imagine this being like a bridge, every time someone buys a house, it means someone sold a house. So the specific individual people are changing and moving constantly between the two, but the total number of people on each side stays the same. So if we give another example. So at the moment, if I've read the news correctly, there's only 50 people allowed inside Tesco at the moment. So we've got all the people in Taunton, 50 people inside Tesco. Now there's only ever 50 people inside Tesco, but the people that, the specific individuals that is, changes all the time. One person leaves, means another person can go in. 5 people leave, 5 people can go in. So the individuals are constantly changing, hence the dynamic bit, but the equilibrium bit, because it's staying balanced. Let's try and arrange that a bit better. So equilibrium, because it's balanced, there's always 50 people inside Tesco, there's always the same number of people outside Tesco. But the dynamic part, because it's constantly changing, the amount of people inside Tesco, the amount of people outside Tesco, the numbers stay the same, but who those people are change. People are leaving Tesco, people are going inside. That's the dynamic part, but the total numbers are staying the same. That's the equilibrium part. So where are we going to go next? Right. So now you know what a reversible reaction is, and you know what a dynamic equilibrium is. One of the other things you need to know about, and this will become apparent hopefully very quickly, is how to make ammonia. So ammonia is NH3. It's a gas at room temperature. It's really important. We use it for all kinds of things, mainly fertilizer to help grow food. So we need to be able to make it, and it's a reversible reaction to make it. And we make it using hydrogen, H2, which is a gas, and we make it using nitrogen, N2, which is also a gas. So nitrogen plus hydrogen makes NH3, which is a gas. And we've got a reversible symbol because this is a reversible reaction. Now we need to balance this. So hopefully you can tell we've got 2 nitrogens there, 1 nitrogen here. So we need to put a big 2 in front of that. So now we've got 2 lots of 3. So we've got 6. 2 times 2, we've got 6 hydrogens. How can we get 6 hydrogens over there? Big 3 in front of it. So that's our balanced equation. This is ammonia. Ammonia. You need to know where we get the nitrogen from, where we get the hydrogen from. It's only just a sort of a throwaway one line. The nitrogen we get from the air. 70% of the air is nitrogen, so we separate it from the air. The hydrogen we get from natural gas. So we get we get hydrogen from natural gas, nitrogen from the air. It's a reversible reaction, and we use it to make ammonia. Now, because this is a reversible reaction, it means the amount of the amount of ammonium we've got and the amount of the reactants that we've got, they stay the same. But it means for every time that these atoms combine together, these molecules combine together to make ammonia, and ammonia splits apart to make those. So remember, it's dynamic equilibrium. So the amount on both sides is constant, but the molecules themselves are constantly joining together and going this way, or splitting apart and going that way. Now this process has a name. It is called the Haber process, named after a German scientist called Fritz Haber. He's really, really interesting. You should look at his Wikipedia page. Anyway, so this is the Haber process, and there's something you need to know about it. So you need to remember the conditions for the Haber process. So it's just 3 conditions you need to recall. It happens at a temperature of 450 degrees. It happens at a pressure of 200 atmospheres, so 200 times the pressure that you're on at the moment. So at the moment, you've got 1 Earth's atmosphere pressing down on you. So it's 1 atmosphere is the pressure in your room at the moment. So this needs a pressure of 200 atmospheres. It also needs an ion catalyst. In a later topic, you need to be able to explain and justify all of these. I'm not going to go into that now. All you need to know at the moment is this is what the conditions are. So this is the Haber process. Nitrogen plus hydrogen makes ammonia. And when we do that, we use 450 degrees, 200 atmospheres, and an ion catalyst. And the last thing we're going to go through in this video today is this. So you need to be able to predict how the position of a dynamic equilibrium is affected by changes in temperature, pressure, and concentration. For that, I'm going to go through and use this example. So people living in England, people living in Wales. So let's say that's an equilibrium. Again, I'm going to make up ridiculous numbers just to make this easy. So let's say 90% of people live in England, 10% of people live in Wales. That stays the same, 90 and 10. But it's a dynamic equilibrium because constantly people are moving from England to Wales, people are moving from Wales to England. So individuals are moving back and forth across the Severn Bridge, but the total number of people in both countries stays the same. So what would happen if all of a sudden we made houses in England incredibly expensive? So if it was ridiculously expensive to live in England and very, very cheap to live in Wales, then the position would shift. Instead of being 90% of people here, 10% of people here, people would look and go, hold on a second, I can get much bigger house, much cheaper there. More people would shift and move across this way. So we'd end up with maybe 50% of people living in England, 50% of people living in Wales. So if we change the price of the houses, it shifts the equilibrium. Shifts, if you imagine it like a giant seesaw, it would shift it. So instead of being, let's say that way, seesaw with 90% of people there and 10% of people there, if all of a sudden we make it look much, much, much more attractive to live in Wales, the equilibrium is going to shift and we might end up with only 20% of people on that side and 80% of people over there. So that's what the position of an equilibrium is how much, what percentage is on each side. So that's explained in terms of how you change the if you change the conditions of something, you can change the balance, change the position of the seesaw. And you need to look at and know how the position of a dynamic equilibrium is changed by temperature, pressure, and concentration. So just to go through those three things. So the first one I'm going to look at is temperature. Now, you need to know, you don't need to know it by name, but I will write it down. So we have got the Chateliers principle. So Le Chatelier's principle is all about dynamic equilibrium, and basically if you change something about an equilibrium, it doesn't like it and it tries to resist the change. So whatever you do, it tries to do the opposite. So if I go back to our Haber process, so we have got N2 plus H2 goes to NH3. Two of those, three of those. Now, the forward reaction, we can talk about these like a forward and a backward reaction. So that's the forward reaction, that's the backward reaction. The forward reaction is exothermic. It gives out heat, it increases the temperature. So I'm just going to put plus heat. So when we do this, when these two shift to make ammonia, it also makes heat. It increases the temperature. So based on Le Chatelier's principle, the equilibrium looks to do the opposite of whatever we want to do. So if we make the temperature go up, this will shift to try and make the temperature go back down. So if that way makes heat, it means that way gets rid of heat. So if we increase the temperature, the equilibrium shifts that way more. So imagine if it was a 50-50 split, 50% over there, 50% over there. If we increase the temperature, we might end up with only 10% over there and 90% over there. That's the worst 90 anyone's ever drawn. So the same goes for same goes if we decrease the temperature. If we reduce the temperature, the equilibrium doesn't like it, fights back, and tries to do the opposite, tries to minimize whatever change we've done. So we lower the temperature, the equilibrium tries to increase the temperature. Which way is it going to shift to increase the temperature? Well, it's going to go to the right hand side because that creates more heat, which will make the temperature go back up. So again, if we had our 50-50 split, if we make the temperature really, really low, we might end up with 5% over that side and 95% over that side. So Le Chatelier's principle, whatever you do to an equilibrium, a dynamic equilibrium, it shifts to do the opposite. So how is the position affected by change in temperature? Well, if you increase the temperature, it shifts to whichever side takes the heat away. If you decrease the temperature, it shifts to whichever side increases the heat. So that means that's an exothermic reaction, that's an endothermic reaction. So just one more last time, you make the temperature lower, it's going to shift this way to make the temperature go back up. If you make the temperature higher, it's going to shift that way, try and make the temperature go back down. Okay, so that's temperature dealt with. Now we're going to see if we can predict the position of a dynamic, predict how the position of a dynamic equilibrium is affected by changes in pressure. And before we can look at that, there's one very quick, and this is a separate topic on its own, so I'm just going to introduce this very quickly here. Avogadro's law states if the pressure and temperature, so 1 mole of any gas at room temperature and pressure has a volume of 24 decimeters cubed. So decimeters cubed is the same with litres. So it doesn't matter what the gas is, it doesn't matter if it's if it's helium just going round on its own, or it doesn't matter if it's methane going around as a molecule with carbon and 4 hydrogens, H, 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 H. If these are in the same room, same temperature, same pressure, that takes up 24 decimeters cubed, and that takes up 24 decimeters cubed. Now we're going to look at how pressure is going to affect that. And we're going to go back to our Haber process for that one. I shouldn't have rubbed it out. Start again. So N2 plus 3 lots of H2 goes to 2 lots of NH3. State symbols on these, that's a gas, that's a gas, that's a gas. So if we compare both sides, remember, for Avogadro's law, it doesn't matter what the gas is, 1 mole of any sort of gas takes up 24 decimeters cubed. So if we look at that, how many moles of gas have we got over here? So we've got 3 moles of H2, and we've got 1 mole from that. So there are 4 moles of gas on that side, and there is only 2 moles of gas on that side. Going back to Le Chatelier's principle, whatever we do to an equilibrium, it tries to do the opposite. So if we make the pressure really, really high, so we've got 4 moles of gas taking up a certain set of space and 2 moles of gas taking up a certain set of space. If we make the pressure really high, increase the pressure to ridiculous levels, this tries to do the opposite. It tries to decrease the pressure. Which way can it decrease the pressure? It shifts that way, because it's halving the amount of space it needs. It's going from having 4 moles of gas to 2 moles of gas. So if you make the pressure really high, it shifts to the side where the fewest moles of gas are to make the pressure low. If you made the pressure really, really low, it tries to resist. You make the pressure low, tries to do the opposite, tries to make the pressure go back up. How does it make the pressure go back up? It shifts more to favour this side, because it's going to make more moles of gas, take up more space, make the pressure go back up. So if you wanted to make, and obviously if you're in a factory trying to make ammonia, you want to make more of this. You don't want it to be a 50-50 split. You want to make as much of this as you possibly can. How do you make the reaction be more on this side instead of 50-50? You want more and more and more on this side. What are you going to do? You make the pressure really high. So you make the pressure really high. This tries to resist by making the pressure go down. How does it make the pressure go down? It favours this side, which is why, so for the Haber process, we're using a pressure of 200 atmospheres. You use a really high pressure. I mean, it's not crazy super high, but you use a high pressure to shift it more to this side. Why does a high pressure shift it to this side? 4 moles of gas here, 2 moles of gas here. Whatever change you do, the seesaw, the equilibrium changes to try and reduce the effect of it. So we've made the pressure high, it shifts to get rid of the moles of gas. Fewer moles of gas, lower pressure. If we did the opposite, if we made the pressure really low, it shifts and favours this side more. Think of it just when we said earlier on about, and I've rubbed it out, about people moving from England to Wales. If you make the houses really cheap, more people shift to that side. If we make the pressure really high, it shifts to this side to reduce it. If we make the pressure really low, it shifts to that side to increase it. And then the last part for today's, this one is actually one of the easier ones. How is the position of a dynamic equilibrium affected by change in concentration? So exactly like we've been talking about, Le Chatelier's principle, whatever you change, it tries to do the opposite. So if we increase the concentration of one of these, the equilibrium shifts to try and get rid of it. So if we all of a sudden put in loads and loads and loads and loads of ammonia, the concentration of ammonia would go up. So this is going to shift the seesaw to that side to try and make the ammonia go down. If we suddenly dumped a whole barrel of nitrogen in there, the amount of nitrogen goes up. So we've got loads more nitrogen. Which way is this going to shift to get rid of the nitrogen? It shifts to the right-hand side to make the level of nitrogen go back down. So just to summarise, we've got dynamic equilibrium, reversible reactions. Knowing what the reversible reaction means, you need to know about the Haber process, which was this one, the reaction we've been talking about. What does dynamic mean? It means it's constantly shifting. What does equilibrium mean? The amount's in balance. You need to know that one, and you can rewatch the video, so I don't know even why I'm talking. Hopefully this made sense to you.